Welcome to Algebra 2, Lesson 10.3, Part 2. So we're starting in the middle of the lesson. If you haven't already completed Part 1 and know a little bit about the unit circle, then this part's going to be a little too much for you. So make sure you've got 10.3, Part 1, Part A done already. All right, to start with, I put this warm-up up here. It's completely up to you if you want to do it or not. It's a little refresher from that other lesson. Number 4, you can solve that any way you would like. We're actually going to use reference angles today. So if you don't know what that means, that's okay. But see if you can solve that. So pause the video, solve it, and I'll be right back with the answers. Okay, here are our answers for the warm-up today. To convert from degrees to radians, you multiply by pi over 180. From radians to degrees, you multiply by 180 over pi and reduce or clean up those answers. Using the unit circle, you'll just locate the spot where 4 pi over 3, the angle, is, and this first coordinate is cosine and the second coordinate is sine. So the answer is just this number right here, square root of 3 over 2. For number 4, there's a bunch of different ways to do this. You can basically do it the same as we did number 3, or you can also just notice that that's a pi over 4 kind of angle. So it's basically like a 45-degree angle. And we know that at a 45-degree angle, the point would be square root of 2 over 2, comma, square root of 2 over 2. So sine and cosine are both that. But because 3 pi over 4 is in the second quadrant, that means I'm going to have a negative x and then a positive y. So my cosine will be negative, my sine will be positive, and when I divide those, I'll get a negative tangent. So the final answers are over here on the right. All right, let's begin today's lesson. We are going to use reference angles. So we did this back in lesson 10.1. We learned what a reference angle. So a 30-degree reference angle can happen in quadrant 1 where we have 30 degrees, quadrant 2 at 150, quadrant 3 at 210, or quadrant 4 at 300 degrees. All of these have a 30-degree reference angle. And if you notice on the unit circle, the points are all the same. The only thing that changed is their sign. So if you can figure out which quadrant you're in, you know what your signs are going to be. And if you can figure out that it's a certain reference angle, 30, 45, or 60, you know what the number will be. So you can answer those questions quickly. So on the unit circle, we know in quadrant 1, everything is positive because our x is positive and our y is positive. When we go to quadrant 2, when we write a point in quadrant 2, we're going to have a negative and then a positive. And remember, the first one is cosine and the second one is sine. So sine is positive, cosine is negative, and if I divide those two, I will get a negative tangent. In quadrant 3, we have negative points, negative, negative. So sine and cosine are both negative, but if I divide those two numbers, negative divided by negative, it's positive. And in quadrant 4, we have a positive and then a negative. So the cosine is positive, the negative, sine is negative, and tangent is negative. Now on your unit circles that I had you complete, there were these little things up in the corner. That's what that was for. So in the first quadrant, you can put everything as positive, or you can put sine, cosine, and tangent, and nothing is negative. In quadrant 2, we said the x-coordinate is negative, the y-coordinate is positive, and when I divide those, I will get a negative tangent. So that's what this is for. On this one, only tangent is positive, and in the fourth quadrant, only cosine is positive, and then sine and tangent are negative. Now, to help you remember that, and one little saying that I've heard, and if you watch some of the videos, you may have seen this, but all STC. So the little saying, which is not necessarily a true saying, is all students take calculus. So if you remember that, you can remember which things are positive or negative. This is also true for the inverse trig ratios. So if sine is positive, then cosecant will be too. You don't need to write all those down. But if you just write the first 3, that would be fine. So if we were in class and I was having you do the unit circle test, which would be memorizing it and plugging in the numbers, you would fill in all these numbers and these 4 corners. So try that. Maybe try testing yourself again on the unit circle and see if you can fill that in. All right, now why is this useful? Because we can answer questions like find the sine, cosine, and tangent of 330 degrees. Well, I know 330 degrees has a 30-degree reference angle. So if I think about my unit circle at 30 degrees, what is that point? Personally, I like the hand trick, which if you didn't see that before, you put your thumb right here and then you put your fingers out here. And that's my fourth finger. So I would put my fourth finger down and the 3 comes first. So square root of 3 comes first. And there's only 1 left over after the finger that I put down. So 1/2. Anyway, that's the way I remember the 30-degree angle is this. Now I know this is 30 degrees, but I am in quadrant 4. So since I'm in quadrant 4, when you plot a point in quadrant 4, you go positive and then negative, comma, negative. So I know this one's positive and this one's negative. Now that I have this point, I can answer any question I want. Sine of 330 is negative 1/2. Cosine of 330 degrees. I should put degrees every time, but I really don't do that. Is square root of 3 over 2. And tangent of 330 is, well, when I divide those, I'm going to have to divide those. What do we get? So sine divided by cosine would be negative 1/2 divided by square root of 3 over 2. When you flip those over, the 2's are always going to cancel. So you could just cross them out right here if you wanted. And you can see that you're going to get negative 1 over the square root of 3, but we don't leave square roots on the bottom. So the answer is negative square root of 3 over regular 3. And there's my final answer. And so I didn't have to use my unit circle to get over here. I just kind of did it in my head. So that's kind of the difference in this. If you're always using your unit circle, you're not going to understand what I'm talking about when I say use a reference angle to find the exact value. You're really trying to do it now without looking at your unit circle. So let's try this one. Well, 270, that's not really a 30, a 45, or a 60. So when it says use a reference angle, I don't necessarily use a reference angle because I know this point down here is 0, negative 1. So I'm not going to need to use a reference angle. Anyway, let's find sine, cosine, and tangent of that one real quick. So sine of 270 is which coordinate? And cosine is the x coordinate. And tangent, what happens when you divide negative 1 divided by 0? Remember, if the 0 is on the bottom, it's undefined. If 0 is on the top, it's 0. So those can, like if I had cotangent here, it would be 0. If I had tangent, it's undefined. So be careful of those. 0 on top is 0. 0 on the bottom is undefined. How about 11 pi over 6? This one's in radians. So we have to think about radians. Well, if it's 11 pi over 6, then it's the same as pi over 6. Because if it's got an over 6, then it's one of these four, like all the 30-degree reference angles have a 6 on the bottom. All the 60-degree reference angles have a 3 on the bottom. So they're kind of backwards that way. So if you think about pi over 6, we actually did that one a minute ago because it's the same as a 30-degree angle. So a 30-degree angle is square root of 3 over 2, comma 1/2. Because I'm in the fourth quadrant, this one's negative. And so I would have, if this is negative 330 degrees, is the same thing as 11 pi over 6. So my answer to that previous problem is the same. I'm going to move on. You can flip back to that other one if you need it. And guess what? This is exactly the same angle too. So when I put my point up there, this is a 30-degree reference angle, but because I'm in quadrant 4, this one's negative. So I've got sine is negative 1/2, cosine is square root of 3 over 2, and tangent is the negative square root of 3 over 3, just like the previous couple problems there. All right, last part of this lesson is using the unit circle to find arc length. So this is going to feel a little bit like geometry when you have a circle. Let's use my drawing, and you want to find the measure of an arc. A curvy spot there. Well, in geometry, what you did is you took 360 degrees, 360 degrees, and let's see, you made however much you had here, let's just call this x degrees. So I'd take my degrees out of 360, and then I would multiply it by the circumference. Well, the good news now is that since we are doing things in radians, this is why radians are useful, we can just use radians times the radius. Radius times radians is going to give me the length of that arc. Because remember, my radius is related directly to radians. That's why the word sounds so similar. Let's try a problem. You'll see what I mean. You need to know this little formula. S equals R theta. Super simple. Not always easy to remember. Basically, it's the length of the radius times the angle is going to give you the length of this S arc. Okay, here we go. First example. A tire of a car makes 653 complete rotations in 1 minute. So this car tire is spinning around and around and around and around and around. So we're not just finding a little arc length, we're finding a huge arc length of it going around. How? And the diameter of the tire is 0.65 meters to the nearest meter. How far does the car travel in 1 second? So we have to be a little bit careful of units. We've got minutes and seconds, so we're going to have to be careful there. The diameter is meters, and I want the answer in meters. So the good thing is I don't have to change that one. So let's start out with finding the radius of the tire. Radius is, because remember my formula is S equals R theta. So if I can figure out R and theta, I'm just multiplying them together. So the radius, well, they told me the diameter is 0.65 meters. So all I have to do is divide that by 2, and I get 0.325. So now I've got my radius. Now let's find theta. Theta is the angle through which the tire rotates. It told me it went 653 rotations in 1 minute. So I'm going to write that down. 653 rotations in 1 minute. However, how far is one rotation? Once around the circle in radians is 2 pi. So 2 pi radians is 1 rotation. So I don't really need the units of rotation. I can just cross that out. Now my only other problem is that this is in minutes. If the units were good, I would be done here. But since this is in minutes and I want my answer in seconds, I need to get rid of minutes and turn them into seconds. So there are 60 seconds in 1 minute. And that will get rid of my minutes units. And now my units will just be radians per second, which is what I want. So my angle is 653 times 2 times pi divided by 60. I'm going to write that out. 653 times 2 pi over 60 is, I've got a calculator here, 21.76 repeating. 21.76 with the 6 repeating. And that would be radians per second if we were doing units here. Radians per second. But I want to know how far it went. That's not a distance. That's an angle. So now to find the final answer, I'm just going to take S equals R times theta. On the next page, S equals R times theta. Now my S was 0.325 meters. Theta was 21.76 repeating radians per second. So that's my angle. Oh, did I forget the pi? Don't forget pi here. I didn't do the pi, so that's times pi. I just did 653 times 2 divided by 60. So 21.76 pi. And then I can just multiply those together. Since this is a story problem, I'm just going to multiply it in and round my decimal. So my answer is 22.2 units meters per second. So that's how far this car is traveling. They rounded it to the nearest whole meters per second, but that's okay. Oh, it said to the nearest meter, so it'd be 22. Remember, it's going around. I mean, this is a car with the tire spinning, so it's going around really, really fast. 22 meters per second is pretty far. All right, let's try one more because that might have been a little confusing. This one is a clock. So we've got a giant clock, Big Ben or whatever. The minute hand is 14 feet long. To the nearest tenth of a foot, how far does it travel in 1 little minute? So we're going to try to draw 1 minute little segment here. You'll have to bear with me on that. All right, first of all, what is the radius of this clock? Well, it told me because the minute hand is 14 feet. That's what I'm using. I want to know how far the minute hand, the tip of it, moved. So 14 feet is the answer for radius. Radians, how far of an angle is this? Well, we have 60 minutes in an hour, so it's 1/60th of the way around, and all the way around would be 2 pi, so I just divide that by 60. So 2 pi over 60 is pi over 30. I'm just going to leave it like that. That's my radians, and that is in 1 minute. So how far did it travel in 1 minute? We can just do S equals R theta. S equals R theta. R was 14. Theta was pi over 30. So I'm going to type this in my calculator. And we get answer in my calculator is 1.466. I'm going to round that to 1.5 seconds. Oh, that's not the right units. Let's fix our units. How far did it go? That's not how long did it take. It should have taken 1 minute, right? How far did it go? It was feet per minute. Yeah, that makes sense. Feet per minute. Where did I get seconds from? Feet per minute. Well, we know it's going in 1 minute. So how far did my little minute hand go? Right here. Since Big Ben is so huge and this is 14 feet, it's going 1.5 feet in 1 minute. And then all the way around would take us around its whole circumference. All right, just to add a little challenge to this problem, since we know we got 1.5 feet per minute, how fast is that in miles per hour? If you'd like to answer this question, go ahead and pause the video. And I did it on the next page. All this is dimensional analysis, where you're changing feet into miles and minutes into hours. So try that out, pause the video, turn the page. I'm the one that turns the page. Here we go. So I have 1.5 feet per minute. Need to turn the feet into miles and the minutes into hours, and we get 0.017 miles per hour. So that's how fast the tip of Big Ben's minute hand is going. And that concludes lesson 10.3 part B. So you may now get going on your homework. Let me know if you have questions.